totally.
Yes.
Perfect. My speech is like a complimentary speech at quite a high level because it's an ontological approach and it tries to cover the concepts. So the semantics is always very useful for the conceptualization of the things. So this is also a part of my secondment here in Tallinn. So throughout the about 3 months, we focus on these ontologies and semantic backend with the researchers of AI for Sec and my team, basically. This will also be a kind of, like a interim report of my studies in Tallinn. So in this presentation, I will focus on the ontologies and semantic web, because usually this is a philosophical topic indeed, and mostly driven by the social scientists and philosophers centuries ago. But in recent years, especially in the last 2 decades, the computer scientists, and in the last decade, by the computer scientists, this topic has also become quite famous. And with the recent advancements in the large language models and new booming AI algorithms, this topic has also become forward. I will start with some basics because we have some young researchers as well. But on the other hand, it seems many people, especially in the hardware domain or in the mechanical engineering domain, the experts, even at very high level experts, they can be quite blind to this topic because we usually get inside these, engineering topics and we forget the big picture. So this semantics let us see the big picture and model it in the way the computers understand. So I will also talk about the knowledge graphs and the ontological approach about the predictive maintenance in the teaming project, and I will also give some updates about the studies. And the teaming objective, the second objective, is about the optimization of the powertrain elements lifetime. And here there is a keyword called trustworthy digital twin, and we believe that the semantics and the ontologies is also a baseline, like a data model of this trustworthy digital twin. So we really address this objective in our studies. So what is ontology? Ontology is defined by Gruber in the 90s, is an explicit formal specification of a shared conceptualization. I add machine readable and domain related because since we are scientists and engineers, we have to make the computer can read these ontologies and all these relations. And the semantic web is a common framework allowing the data to be shared and reused across different domains, applications, enterprises, or communities. So it has many boundaries. We as the humans, we have the brain. This is a kind of a big ontology inside already, loaded by default when we born, and then it improves day by day as we grow up. So this is a kind of
Voice is gone again.
Alper, we can't hear you. I think you mute the microphone. Alper, we can't hear you.
Can you hear me again?
Yes.
Yes, we can hear you now.
Yeah, where were you left?
So
This
I think
presentation.
in the last 2 pages, Alper.
So, are you okay with the motivation scope? I think it's okay.
Yes, okay.
Okay, so let me continue from these ontologies. Sorry for the inconvenience. So I was talking about the ontology before the system shoot me out. The ontology is an explicit formal specification of a shared conceptualization. Sorry for the repetition, but I add the machine readability and domain related things because we have to teach these computers this big ontology, and they should read it, and it should be domain specific. And the semantic web, this provides a common framework that allows data to be shared and reused among the applications, the domains, and different boundaries depending on the topic. So here in this presentation, in this slide, I will start with the main, things about the ontology, because this is usually being ignored or somehow not addressed by the engineers, because we usually focus on the deep details about this, the big systems and the engineering stuff. But in the meantime, we forget the meanings. I mean, the relationships among the entities and why we are doing this. And semantics helps us creating this philosophy behind and the rationale behind, and models the relationships between these entities. A typical ontology has a common language that is formed of symbols and expressions. This is called syntax. And these symbols and expressions have their meanings, and it is called semantics. And these symbols and expressions are grouped in classes. We call this conceptualization. We try to put things together. This is also the way our brain does, because when we have many data coming from the outer world, we have our own senses, like eyes, like ears. We hear many things, but we have to group things. When we group these things, we can manage those data more easily. So there also exists, if we have a hierarchical data, things become easier. So this is called taxonomy. So if we have a taxonomy, we can model the systems better. But in general, these taxonomies, like in tree format taxonomies, are not enough. We have to think about graphs rather than the trees. So these ontologies, these data models come together with different relationships among each other. And the final thing is, implicit knowledge can be made explicit. So this means we need a reasoning mechanism. So this reasoning mechanism is usually ignored in the current AI studies. People are trying to do some stuff. The mainstream AI deals with the data, training the data. They're trying to recognize something. This is very useful. But on the other hand, especially with the recent advancements in the large language models and other things, this reasoning becomes more on the ground. So what are the level of knowledge? So at the very lowest level, we have the conventional databases dealing with the object, structure, classes, and there exist some loose relationships among these things. We have some identifiers linked with each other, so we have these tables of classes and then many things. But in real life, it is quite easy, it is quite hard to manage a very huge amount of data. So you should create millions of classes, millions of tables to model this data. And it's really time consuming and not easy to manage. So at the very, and above this, we need another framework called RDF, usually called RDF, Resource Description Framework. This becomes, presents some knowledge about these objects, meaning that it creates more links between these entities. But this is again not enough because we have to cluster these knowledge groups. So here the ontologies in the OWL format comes into ground. They say that we need domains. So we cluster these entities among each other and then link with them. And at the highest level, this is quite a new topic in the last 2-3 years, the knowledge graphs. So these knowledge graphs, they try to define some interconnections between these clusters. So by creating this, we come up with more extended understanding of the concepts, and we can go deeper as much as we want. In the automotive domain, there exist many domain ontologies. Auto is one of the biggest ones. So they mainly focus on the road vehicles, their configurations and characterization. But in general, there exist some domain-specific ones dealing with autonomous vehicles, ADAS systems, or predictive maintenance or driver experience. So what we learned from the literature, since the automotive is a very huge area, we need some special purpose and targeted domain ontologies. Otherwise, we need a very dense semantic engineering work to extract some correct links between these graphs and these concepts, which is really not easy. So we have to start from quite bottom up, I mean, from the domains and integrate them at a higher level. So here you can see a very simple example of an ontology in the automotive domain. This is not a full ontology for sure. This is just for the example. But here it starts with the main think. So this is the think. Everything starts from the think. So we have the human and we have the road vehicle. A human can be a driver, passenger, or an expert in our domain. And the expert can be a designer, a mechanic, or an engineer. A road vehicle can either be autonomous or non-autonomous, and it can be an electrical vehicle, a combustion engine vehicle, or a hybrid vehicle. If it is an electrical vehicle, it can be a battery electric vehicle or a fuel cell electric vehicle. So you can extend this to a wider scope, but just as an example here, you can see the main classes. So these are the main called concepts. So think, human, road vehicle, expert, these are all classes in a typical ontology. And we have the individuals. I mean, these are the instance. For instance, 4T model is an individual of the class non-autonomous road vehicle. And we have the taxonomy, so we can present the hierarchical representation of some classes. But this is very applicable. I mean, this is not limited to. For instance, on the left-hand side, we have a tree-like structure, but on the right-hand side, we have a graph-like structure. And we have the attributes, like properties, describing an object. Like 4T model has many attributes. For instance, it has a name, it is a model, the manufacturer name. It can be owned by some person or something. So these are the main attributes in a typical ontology. And beyond this, we can also describe the relationships. These are called associations or predicates. So you can see some example predicates. The most common one is the is-there relation. Like road non-autonomous vehicle is a road vehicle. or designer is an expert. So these are the widely used ones. And HESE also is another widely used predicate, like electrical vehicles, they have some batteries. So this has a relation. But we can also create our own predicates, like drives or designs or maintenance, depending on the role. So we can create some sort of triples. These triples are called subject, predicate, object triples. For instance, autonomous vehicle is a road vehicle. So this is a triple. We can also define some restrictions. For instance, we can say that road vehicle can only be maintained by an authorized mechanic. So this becomes, this brings a new predicate called authorization. So we can extract some rules, and differences can also be defined. Like we can say that driver is not a passenger. So this is true according to our domain. And axioms can also be extracted, like autonomous is a road vehicle. So we can say that all autonomous vehicles are road vehicles in our domain. And one step further is the knowledge graphs. So a knowledge graph, first it's a database. So the ontology tries to model the things. I mean, road vehicle is an autonomous vehicle. So these are like at conceptual level. But if we say that Tesla is an autonomous vehicle by this type and etc., so we can extract some instances about this. So all these things are modeled in a knowledge graph. So this is widely used in the LLM world. And this brings us a big graph of this, data. This can also be extracted from an ontology, come up with a knowledge graph, and then we can generate some data out of it. This is what the ChatGPT does, for instance. For sure, this is still a recent topic and very open to research, and maybe we can also go deeper in the teaming project. So here in the top, this was the procedural era. It is quite old because in the 10 years ago, maybe, or 5 years ago, people were working on the raw data and they tried to extract some rules to come up with some decisions or answers. So this was we have a procedural code. And then the machine learning era started. Then here we had the raw data and answers, and we trained the systems to come up with these rules. And now the knowledge graph era is starting. So we have the raw data, we have the machine learning algorithms, we have these big models, and we can use them to extract some knowledge out of it, some answers out of it, and also explanations out of it. So here we can ask some questions. Why don't we consider this security and privacy preserving heterogeneous data streaming? So this is not only textual data. So if we are dealing with some cyber physical systems like the electric vehicles, we have many IoT nodes as well. We have many internal and external systems in these vehicles. And why don't we improve these systems with explainable and trustworthy AI? This is also another topic, because when you go to a maintenance worker, they are not well trained in this topic. So we need some more explainable things, as Ali Serdar mentioned in his speech. So these topics form our ideas about for the teaming project. So what we aim in the teaming project, first of all, we want to focus on a PdM oriented and predictive maintenance oriented ontology, and integrate this with the IoT in cybersecurity. So smart sensor network ontology is a widely used ontology in the IoT domain, and ENISA threat taxonomy is a widely adopted one. We can rely on this threat taxonomy, and we are planning to create an event ontology out of this. So this will address the security aspects of the problem, and we can ask some smart questions. These are called smart queries in this ontology domain, like this man-in-the-middle attack, for instance, may cause a maintenance problem, a safety problem. This can be either predicted or not predicted. So we can at least ask some questions, some smart questions, and we can find answers to these questions. And the second thing is we have already started implementing a cyber resilient cloud backend strengthened with this hardware-based security, as Salih mentioned in his speech. We are planning to use those technologies in the backend and try to apply some semantic data brokers based on Virtuoso. This is a common and widely used triple store. And by using these, we are planning to integrate these technologies over some edge nodes, especially on the vehicle. Thanks to our colleagues, especially in AI4Sec, maybe we can improve this with large language models and semantic AI for more trustworthy EV-enabled services. So the first step will be, for sure, from ontology to knowledge graphs. In our first round of studies, we identified a good ontology from a legacy project, from a Horizon project called ZBreak. So ZBreak ontology is selected as the baseline because it is easy to manage, and it's not a very huge ontology, and it's easy to understand, at least for ourselves. It has 55 classes and 54 object properties. And it can model the system parts, embedded data sources, failure modes, symptoms, and maintenance actions. And it can also define some severity indicators. So this gives us an overall PdM data model. So we can use this as a baseline and adapt this to the predictive maintenance problem in the automotive domain. You can see some triples, like the one is system part role. So we have the cooling fans as the system part. We have the system part failure mode in this ontology causing a block, for instance. System part failure symptoms can also be identified, like local abnormal noise or vibration. These are some symptoms. We can identify some majority levels for the severity and relate them with some part of the vehicles. And the predictive maintenance process definition can also be defined. So this is the graphical representation of the ZBreak ontology. As you see, the tree-like ontologies is not applicable usually in real life. So it gives us a very good baseline, but we also identify that it's not enough, because the IoT security are not directly addressed, and the automotive domain is not directly addressed. So we need to improve this with some domain ontologies, and the safety topics are partly addressed. So in the teaming project, we will have many safety concerns to be defined by the other parties as well. So we can add them in the ontology. The good thing about the ontology is that it is really flexible. You can improve it. You can extend this with new concepts, with new classes, and relations. And embedded and out vehicle data sources need to be addressed, because it should be IoT enabled in the meantime. And we need a more focused approach for the powertrains and EVs, which is the core topic of teaming. So, and this is a block diagram of the semantic backend. So we have the triple store Virtuoso, and on top of it, we have some other utility tools developed in Java like Apache, Jena, and for the repository and the ontology classes. And we are using REST APIs for the main CRUD operations and the services orchestration, and also SparkQL engine that makes us to create some smart queries out of this. And on the right-hand side, as Ali Serdar presented in his speech, for the cloud backend, we have the IoT middleware, communication and automation layer at the cloud implemented in IOFOG and Arrowhead. At the enterprise level, we have Mimosa, and at the high level, we have the visualization and interaction layer. And all this stuff form the backend of the digital twin implementation strategy in the teaming project. So what are the future studies? The ontology integration and development of the semantic AI backend will be our top priority. And the development of the IoT and hardware-based cybersecurity backend and its integration over the cloud will be the second step. As Ali Serdar presented in his speech, the integration with energy efficient, trustworthy and explainable AI and maybe LLM algorithms will be the next round. And since this is the spirit of teaming project, we will contribute to the training and dissemination activities throughout the 4 years of the project duration. And before finishing, I would like to mention our special thanks to AI Force Tech for hosting us in Tallinn. And my team, ERARGE, so this is the sending organization, especially Salih Ergun, the CTO of the company, and my colleagues who helped me a lot throughout this journey, and Professor Reich and Taltech researchers for organizing this workshop. If you have any questions or remarks, please do not hesitate. Any questions?
I have a starting question. So this Z-Break, this is developed by whom, and what are your plans? You plan to extend it now to
Yes.
this application?
This is the good thing about Z-Break is an open source, so you can easily find it. It is developed by a consortium. I think it was led by ETH Zurich as well. So they were one of the most active partners. So yes, we have to improve this because it is not enough. But it gives us at least the overall predictive maintenance strategy and the relationships. We can, some add new domain stuff, some domain ontologies, or we can add some new classes because it's really flexible. So we use the Stanford's Protege tool to improve this ontology, and it generates the OWL files. And the next step is to develop the classes about this, and then the development process continues. Yeah, so you can easily find it in the by just googling. Any questions or comments?
Maybe one of the question is again me, but one of the questions is, so in this project, so do you plan some use cases where it's linked to some of these research tasks of the partners? Like,
Yeah. These Marie Curie projects are quite different than the research innovation actions or innovation actions. Those projects are usually demonstrator driven, but this project also has some industry perspective. So in this again. So sorry for the inconvenience. Yeah, I'm back again. Can you hear me, the audience?
Yes, yes, we can now hear you.
Okay.
Yes.
Perfect. Perfect. So yeah, Teams usually throws me out. I don't know why, but um, what was the question? Sorry, I forgot.
The question was about these practical applications of this.
Yes, the use cases. Yeah, the use cases of the teaming. Yeah, teaming has a very strong motivation to apply these technologies in the automotive domain, especially since CA is involved in the project, so they are the coordinators. They have very strong links with the automotive industry. So the use cases, there will not be a direct use case, but all these technologies are planned to be applied in close contact with the OEMs. For instance, we are also in close contact with Autocar, although Autocar is not involved in the teaming project. We are planning to share the outputs of the project with them. We have already started to, as Salih mentioned, but the use cases, there will not be very, targeted use case, but more advanced research, cutting-edge research, and its potential applications in the lab scale domain. Okay. Any question or remarks?
I see that Ali has an.
Yes, addressing to the comment from Jan, also to Alper. I believe it doesn't. I mean, yes, Alper is completely right about the teaming, but in general, there is a great appetite, as I see from our colleagues from CEA. Not only here in this project, but many other projects, there exists a need about this, like safety, reliable, explainable. And easily usable, I will say, solutions for the automotive sector. And so I believe we can create a use case together with the LLMs, as we were discussing, and we can basically create an ontology through the LLMs with the knowledge graphs, what Alper just explained, and we can create a nice user interface. Because we have some great UI experts like Ömer. He can do that, and we can maybe get the help, get the guidance from the experts like Vincent, like his input about this. What can be the best applicable architecture, the algorithms for the deployability, and we can turn this into maybe early product, early prototype. I think why not? I mean, partially it can be contributed to teaming, but partially the other projects that we can work all together. I think Jan also mentioned the requirement from ARM, the need from ARM about the safety of this, of their research. So I think we can explore that, Alper. I mean, although teaming, it can be a lower level TRL work, but I think we can all explore the adaptability and the usability of all these things, all this great work.
Mm-hmm. Thank you very much, Serdar. So we are quite behind the schedule, but I think we have five more minutes to have some short brainstorming. First, let me start by asking if there exists any question from the audience about these presentations or any remarks on these topics. So, if not, I have one question to Jan about the standardization topics, because I know he's very active in this domain. So, Jan, how do you see the future of this standardization activities in the automotive domain from your perspective? Maybe you can come here.
Yeah. So maybe we can even grab chairs and sit here. I don't know, or stand. So yeah, so we are just joining this ISO standard, but we had an I was I have had some briefings about what is going on there, and basically this ISO 8800 is there's still a lot of open questions because it's kind of like tries to build on this 26262, but now we have a standard for machine learning like systems where we have also data as part of the standard, and basically the status is that in fact they are building the ontology for the standard. So they have the data, they have the task, and they have the ML system, and so they kind of like are building the ontology. But in fact, as of now, there is no working example for that standard. So there are like 13 countries and several tens of institutions working there, including ARM and the automotive companies. But currently, when I was looking at the ontology stage of this presentation, it's at the ontology level. There is no concrete subsystem where this has been applied. But the point of this standard is to tackle the AI part that is now being part of the automotive, right? So we have even as of today, we have these driver's assists and all these kind of things. What is safety guarantees for these kind of things? Mm-hmm. But also we started with this process of joining this committee in April. And we were following this presentation by Simon Burton, who is leading this standardization committee. And due to some local bureaucracy, I am still waiting for the one signature to join this standard. So we had here in Estonia a lot of delay with first to be approved as part of the standard. So I still haven't seen the documents, unfortunately. Yeah, but I just know from the presentations what I've heard. So I haven't seen the whole documentation yet.
So it seems that we still have many empty rooms to be filled.
Absolutely, because I mean, even from the use case perspective, there is no use case at that point. Mm-hmm. There is no use case, and during the date conference in April, it was said that the standard will be published in the middle of this year. But I mean, based on what I've heard, I think there are going to be some delays. Yeah. So. But we're trying to find out. So we're trying to, as soon as possible, get access to all the materials.
Mm-hmm. This was also mentioned in the ECS brokerage event in Brussels, Electric Components and Systems. So they are now managing the EU Chips Act. So these standardization topics were, highly addressed in all these topics as well, including the automotive domain, but not only the automotive domain. I mean, there is other stuff to be needed. And one more thing is about the hardware-based security and reliability topics, as Levent mentioned and Salih mentioned. And they also press on the use of open cores. I mean, like RISC-V is just one of those. And also the open hardware and open software solutions. So do you or maybe Levent or Salih, do you have any expert
comment on this?
If you have any comments, we'll be very pleased. So how do you see the future of these open innovations and open source
regarding hardware security?
There's a lot going on, especially with RISC-V.
And maybe you can come to front. Oh, Mike is here, so you might not hear.
Yeah, Sam is also. Yeah, maybe you can introduce yourself.
Sure. I used to be a professor here at Caltech. Now I'm a professor at Carnegie Mellon in Pittsburgh. And yeah, my topic of expertise is hardware security. So the question was about these ecosystems that exist for open source hardware, and RISC-V is by far the largest. And when RISC-V started, it was an exercise on computer architecture, and it didn't have security in mind. But there are many extensions to RISC-V being proposed by different groups that add security components to RISC-V. Sometimes it's very little things like support, native support for cryptography, some specific instructions that do cryptography for you. Some other things are much more robust, like we need a generator of random numbers that is reliable and has to be part of the processor somehow. We need some sort of signature. We need some sort of trusted memory storage where you can put your keys or identifiers of any sort. All of that is growing out of RISC-V.
When you say random numbers, we have also a big expert. Salih, can you hear us?
Yes, yes.
Maybe you can comment on the use of true random number generators, especially in the automotive domain, but also in other domains. How do you see the open innovations and the true random number generators?
Actually, sorry, Salih, just a comment to this is that Sam arrived after your presentation, so he didn't see what you were presenting, but it's actually in line.
Okay. Also nice to meet you too. So if you want to use a open source or open specific hardware, of course, security is the becomes one of the most important topic actually. So we are designing different kind of random number generators, true random number generators, and also this is a sophisticated topic. So the question is what is random? So there is nothing random but uncertain. So I mean, if you observe something, then you can control it. Then this is not random. So there are some philosophy inside this random number generation, but I mean, we have actually focus on if you use a open specification hardware or open source. So we focus on 4 criteria to design a random number generator. So the throughput of a RNG must fulfill all statistical tests. The next and previous bit must be unpredictable, and the same bit sequence must not be reproduced. And the 4th one is the RNG must be robust against all attacks. So we generally follow these 4 perspectives, but we first design the prototype, then we crypto analyze, we also apply vulnerability analysis methods. Then I mean, our design become more robust in comparison with the initial version. Then we finalize the design actually. So I mean, all crypto algorithms are publicly known, but only the crypto key is unknown. So I mean, we need to design we must design a more robust RNG, as robust as possible, of course. Of course, I mean, time is money, and also design is also money. So, I mean, if you focus on security so much, then your design become more expensive. So there is also drawback here. I mean, we need to apply security as much as needed. I mean, for example, we in the initial version of our security platform, we didn't propose to construct a point-to-point security, but instead of this, we assume the bus itself, a car itself, as a black box is secure and no one can probe this. So, I mean, you need to do everything for this assumption. Then only the open port is the service port or OBD2 port. So we, for example, we propose to mount authentication CAN authenticator to this port, and this is enough for the initial version because, as you know, in the nowadays there are more than 200 microcontroller inside a car. So I mean, if you propose
You cannot
point-to-point security, at that time this become a very expensive solution and it's not applicable for a commercial company.
So there exist many trade-offs, as you mentioned. One is the technology acceptance is also a big problem. So you cannot apply security everywhere. So because the OEMs usually react to this, so they do not want to change everything. And another thing is the energy efficiency. For instance, in our work, we try to develop some true random number generators with significantly less amount of logic gates. Some people are using 100 gates for the same purpose, but we come up with a reliable, trustworthy, and truly random number generators with maybe just 8 logic gates. So this brings us the energy efficiency. And as Serdar also mentioned, energy efficiency in AI is also very important because they want to use these energy efficiency algorithms directly on the vehicle and on the edge. So this brings the energy as another trade-off topic. So these are all, engineering problems that should be solved by the help of scientists like you and researchers like you. So there can be many other things to be discussed, but I think we are running out of time. Do you have a final word to say?
Yeah, I just a final word. So maybe what I did not explain really in detail, or not in detail, but didn't motivate why we actually need this safety certification for AI, is that at the moment of now, you see from the news that some local government, let's say San Francisco board, says that okay, do we allow this self-driving taxi to work in our streets or not? And they vote and they say, yeah, let them drive. So, and then when I was in this safety certification session in Date, there was also, like in Europe, they develop a lot of stuff for automotive and trains, and they say, well, a human driver makes 1% of errors, so we make an AI system that errors 1% of the time. And we have this rule of thumb, and we somehow, pretend that we measure it, or we have a very rough measurement, and then we say, okay, we think we can still put it on a rails, or we can put some autonomous car driving somewhere. But at some point, when these standards are going out, they are going to be mandatory. I mean, you have to you have to apply to these standards. It's like, and then you really have to measure, and you have to kind of guarantee your AI's reliability. And I think we have to be, this happens probably pretty soon. So once these standards are out, they are gradually going to be requirements for the automotive. And I think that's kind of the process where we have to be. Like when I listened to Ali Serdar's presentation, I think a lot that he presented are moving towards that direction, that we can actually explain, we can actually measure, and having this this coloring approach, or this mapping, or how you called it. I think these things are going to matter, because in the end, the car manufacturers and the manufacturers of the systems that go into cars, they have to conform to these things.
Yes. It has already started with these UN regulations, 155. The due date was June, but they extended to the end of the year because many OEMs are still not ready for this. They are really aware of it. So if you don't have any other things to say, maybe we can clap ourselves.
Okay.
Thank you very much for your contributions. And see you in the next workshop, hopefully. Bye-bye.
Thank you, everybody. Thank you.
Bye-bye.
Thank you. Bye-bye. Bye-bye.